Ever felt like some problems need more attention than others? Imagine a computer program that doesn't just work harder on complex problems, but actually changes its approach based on the task's difficulty. It's a new way of thinking in the world of machine learning. And today we're going to uncover what makes AdaTape so special. But before we get into that, make sure you hit that subscribe button and turn on the notification bell so you don't miss any of my future videos. Okay, so first, let's talk about something called adaptive computation and how traditional neural networks, which are a type of machine learning, usually work. You might already know that neural networks are tools used in technology that can learn from information to do things like recognize pictures, understand language, create speech, and more. But the usual neural networks have a set way of working, using the same effort for all the tasks, whether they're hard or easy. That's not great because not everything is equally challenging or needs the same focus. Some pictures might be fuzzier, some sentences might be trickier to understand, and some math problems might be more complicated. Ideally, we would want our machine learning tool to change its effort depending on how hard the task is, putting more work into difficult tasks and less into easy ones. That's where adaptive computation comes in handy. It's all about a machine learning system changing how it works based on what it's dealing with. Adaptive computation in neural networks is appealing for two key reasons. First, it provides an inductive bias that can play a key role in solving some challenging tasks. For instance, enabling different numbers of computational steps for different inputs can be crucial in solving arithmetic problems that require modeling hierarchies of different depths. Second, it gives practitioners the ability to tune the cost of inference through greater flexibility offered by dynamic computation, as these models can be adjusted to spend more flops processing a new input. But there's a catch. Existing adaptive models have some limitations and drawbacks that prevent them from achieving their full potential. For example, some adaptive models use conditional computation to selectively activate a subset of parameters based on the input, but this can be inefficient and hard to implement. Other adaptive models use dynamic depth to allocate the computation budget by varying the number of layers or iterations used for each input, but this can introduce instability and complexity in training and inference. Now, AdaTape is a new model that utilizes adaptive computation in a novel and elegant way. It's a transformer-based architecture that uses a dynamic set of tokens to create elastic input sequences, providing a unique perspective on adaptivity in comparison to previous works. AdaTape is like a tape reader machine that reads data from a tape and makes calculations. It can adjust itself to understand various tokens added to the input based on its complexity. And it works with two kinds of tokens: input tokens, which represent basic data like words or pixels, and tape tokens, which are selected from a set of choices called the tape bank. The tape bank holds all possible tape tokens that can work with the model. The system represents each input as a combination of input tokens and tape tokens, changing the number of tape tokens according to the complexity of the input. It turns each token into a vector that captures its meaning. This model can create the tape bank in two ways: an input-driven bank, which takes tokens from the input using a unique approach, and a learnable bank, which uses trainable vectors as tape tokens. The system uses a standard transformer architecture, with some changes to process the data. It includes layers that learn how the tokens are related, and forms an output sequence. AdaTape uses different networks for input tokens and tape tokens to keep their representations separate. Now, the model also performs very good on various benchmarks, and it does better than many top models in areas like image classification, algorithmic tasks, and understanding natural language. For image classification, AdaTape is especially good. It can get high accuracy with less computing power. On the ImageNet 1K dataset, a big collection of images for classification, it gets 83.8% top 1 accuracy with only 86 M parameters and 4.5 B flops. That's better and more efficient than other models like VIT and DIT. AdaTape also works well for algorithmic tasks, like complex arithmetic problems. It is better than other models on tasks like addition, multiplication, sorting, and parity, and it gets nearly perfect accuracy with less computing power. It also has a quality-cost trade-off advantage, meaning it can get higher accuracy with lower cost or vice versa, depending on what you need. Unlike models like the adaptive computation time algorithm, universal transformer, and PonderNet, which change the number of layers based on a halting system and can make things complex, AdaTape uses a fixed number of layers. This makes it stable, and avoids problems with memory and speed. It is also easier to put together than models like mixture of experts models, which pick certain parts to use based on the input. This can be tough to do and can lead to issues in using the parameters properly. AdaTape doesn't have this problem, as it uses all the parameters equally. We're going to explore AdaTape further by looking at how it performs on specific tasks and scenarios. First, let's talk about parity tasks, which are simple problems where you figure out if the number of bits in a binary string is even or odd. While this is easy for people, it's hard for regular transformers because they treat long and short strings the same, which can cause problems. AdaTape is different. It adjusts its approach depending on the string length, using more resources for longer strings and less for shorter ones. This makes it more efficient and accurate, particularly for longer strings. For example, AdaTape gets 99.9% accuracy on a 256-bit parity task, while standard transformers only get 50.1%. Now let's look at how AdaTape performs in terms of efficiency. It provides an effective knob to increase the accuracy when needed, but is also much more efficient compared to other adaptive baselines because it directly injects adaptivity into the input sequence instead of the model depth. To measure the efficiency of AdaTape, we can use two metrics, flops per sample and latency per sample. Flops per sample measures the number of floating point operations required to process one input sample by the model. Latency per sample measures the time required to process one input sample by the model. AdaTape achieves lower flops per sample and latency per sample than other adaptive models on various tasks and benchmarks. For example, on ImageNet 1K, AdaTape achieves 4.5 B flops per sample and 3.2 millisecond latency per sample with 83.8% top 1 accuracy. In contrast, PonderNet achieves 7 B flops per sample and 4 millisecond latency per sample with 82% top 1 accuracy. It also shows a quality-cost trade-off advantage over other models, meaning that it can achieve higher accuracy with lower cost or lower accuracy with higher cost, depending on the user's preference. For example, on ImageNet 1K, AdaTape can achieve 84.2% top 1 accuracy with 5.5 B flops per sample and 3.8 millisecond latency per sample by increasing the number of tape tokens. Alternatively, AdaTape can achieve 82.4% top 1 accuracy with 3.5 B flops per sample and 2.6 millisecond latency per sample by decreasing the number of tape tokens. This means that AdaTape can be tuned to fit different scenarios and requirements. These results show how AdaTape is efficient and flexible in terms of computational cost and performance. So that's all about AdaTape. I hope you found this video